So last time we talked about the reactions of aldehydes and ketones with nitrogen nucleophiles. This time, let's talk about oxygen nucleophiles. And the first reaction we will start with is hydration. We're going to draw this mechanism together. So this hydration mechanism, this particular one, does not have an acid catalyst, so therefore we attack the carbonyl carbon straight out of the gate. And we get this thing. We have one O with a negative, one O with a positive, maybe a little bit illegal, but let's exchange protons between them to get me here. OH, OH. This thing is a hydrate. It's also called a gem diol. Remember the Gemini twins? Diol. The same carbon has two OHs on it. It's a hydrate. Hydrates are always in equilibrium with ketones and aldehydes. This particular ketone exists as a large percent hydrate. This particular aldehyde, I think I just called it a ketone a minute ago, this particular aldehyde is a large percent hydrate when water is around. The keto, it's not a ketone, but the keto form is not as favorable as the hydrate form. Why is that? Well, the greater the partial positive on the carbonyl carbon, the more stable it is as a hydrate. So this carbonyl carbon is quite partially positive because is hydrogen a donor, a withdrawer? No, hydrogen is sort of our baseline. It's not a donor, it's not a withdrawer, it's not anything. It's the baseline. Then I've got a carbon, which is typically a donor, but this carbon has 3 electronegative chlorines on it. So that carbon is actually pulling electron density away from your carbonyl carbon, making it more partially positive than average. So if I were comparing a CH3 aldehyde to this CCl3 aldehyde, and I were asked the question, which one of these has the greatest percent hydrate at equilibrium? What you need to do is judge which one has the greater partial positive on the carbonyl carbon. The greater partial positive means the greater percent hydrate at equilibrium. So this one has the greater percent hydrate at equilibrium. Okay, cool. One thing I need to remind you of before we move along to the next thing is equilibrium constants. Oh, yeah, equilibrium constants. So back in the day of general chemistry, you talked about equilibrium constants are products over reactants. Products over reactants, and water is officially a reactant in this reaction also, but water is not generally included in an equilibrium constant. If you really want to know why, we should chat, but we talked about it in general chemistry. So sometimes you'll be asked the question, which one is the greatest percent hydrated equilibrium? But sometimes you'll be asked the question, which one has the largest KEQ? Which one has the largest equilibrium constant? And that's what KEQ is. So the more hydrate you have, the bigger your KEQ. So big hydrate, big KEQ. Be aware of that question. I think I said one more thing before we go to our slides again, but I lied. 2 more things. This mechanism I said is not catalyzed by acid. This is just neutral water. You could add some acid to this mechanism to catalyze it. You would end up in the same spot overall, but I would suggest protonating your COO oxygen before you attack, and then just some base cleans up. This could also be promoted by hydroxide. Hydroxide attack the carbonyl carbon, and then you neutralize your product. Whether there's acid or base or just plain water, you end up in the same spot at a hydrate, a gem diol. All right, I got it. Oh, I forgot to tell you that the hydrate this forms, look up a Mickey Finn, F-I-N-N, Mickey Finn, Google it. if I compare these two carbonyl compounds, which one has the greater percent hydrate at equilibrium? Remember, we're looking for which one has the most partially positive carbonyl carbon. Aldehydes are more reactive than ketones because they have a more partially positive carbonyl carbon. Remember, hydrogen is our baseline that we compare things to, and then carbons are electron donors. So a ketone has 2 carbon groups, 2 electron donors. An aldehyde has 1 carbon group, so 1 donor and 1 hydrogen, which is not a donor or a withdrawer, it's just a hydrogen. So an aldehyde is more reactive than a ketone because the carbonyl carbon is more partially positive. So an aldehyde has a greater percent hydrate at equilibrium than a ketone. Whew. What about these two aldehydes? Well, the benzene one can actually donate electrons to make things more stable. Those are resonance arrows. They're pretty illegible, I recognize. But the benzene can donate electrons to help stabilize the partial positive on the carbonyl. So again, that makes this aldehyde more reactive, more greater percent hydrate at equilibrium. In the last one, they're both aldehydes. They both have benzene, but the question is this functional group versus that functional group. This, I hope we remember from the aromatic section, is a good donor. So it can donate electrons to stabilize your partial positive on your carbonyl. This nitro is the strongest withdrawer, so that nitro group serves to make this the greater percent hydrated equilibrium. That carbonyl has a more partially positive carbon of your carbonyl than this one. Yeah? Okay. So this one, we're talking all about oxygen nucleophiles. Let's do this with an alcohol oxygen nucleophile. So this one, we're starting with an aldehyde, and we're adding an alcohol. And this one is not acid catalyzed. That's an important note that we will mention in a moment. Not acid catalyzed. Attack the carbonyl carbon, like so. Maybe a little illegal, but I'm going to take a proton, lose a proton to get here. Here. This thing is called a hemiacetal. You're going to call it a hemiacetal probably. I'm going to call it an acetal every time. So this hemiacetal, hemi means half. It's a half acetal. Let's talk about a couple of new functional groups all together. If I have a single carbon that has 2 OHs on it, these other groups can be R's or H's or whatever. Single carbon with 2 OHs on it, that's called a hydrate. We just saw that. It's a gem diol. If I have a single carbon, these other groups can be R's or H's or whatever. A single carbon with an OR and an OH, that's a hemiacetal. If I have a single carbon with 2 ORs on it, that is officially an acetal. So a hemiacetal is halfway between a hydrate and an acetal. It's a half acetal. Officially, it's called an acetal if it comes from an aldehyde. So an acetal really requires that this R be an H and that this R be an H to be a hemiacetal or a regular acetal. If this is actually a carbon group, it becomes a hemiketal because it comes from a ketone or a ketal. I call them all acetals anyway out of bad habits. Do as I say, not as I do. So back to our mechanism. This is a very quick mechanism, certainly way faster than all that imine-enamine mess. This is what happens if I have alcohol. Neutral alcohol, no acid, no water, no acid, no base, no catalyst, just neutral alcohol that can attack to make a hemiacetal. But if there's acid present, things go further. You don't stop at a hemiacetal. Let's go further. So if I start with that same aldehyde that I just drew, and the same alcohol that I just added, but this time I add some acid to the mixture. I'm going to start out by protonating my carbonyl oxygen. The pH of these reactions do not have to be controlled like the other ones we talked about previously do. Why not? Well, because we had a nitrogen nucleophile in the last, we had an amine nucleophile then, and amines are bases. But an oxygen, a neutral oxygen like this, is not going to get protonated to destroy its nucleophilicity, so it's okay to have a lot of acid here. It really only needs a catalyst, but it's okay if you have quite a bit. This time, I'm going to do the step that we've skipped in several mechanisms now, and some base is going to come clean up my H to give me this. This is a neutral tetrahedral intermediate. Why is that important for me to point out this time? Well, this thing is a carbon with an OR, a carbon with an OH. This is a hemi. It's a half-acetal. That thing got a hemi? You should look up that commercial if you don't understand that reference. When you're in acid, you can't stop at a hemiacetal. It's not allowed. Do not pass go. Do not collect $200. Do not stop. You got to keep going. You protonate the OH of your hemiacetal to keep going. This version is not going to make a half acetal. It's going to make a full acetal, a legit total acetal. So you protonate your OH so that you can fold down and kick it out. Could you see that coming? I hope so. Then I have this carbonyl thingy. This carbonyl thingy is confusing because it still has an R group over here. That's okay, but what it means is it's not stable as it is, so another alcohol comes to attack your carbonyl carbon. You get O plus and some base in solution somewhere. Comes to clean up. And all of a sudden, ta-da, you have an acetal. One single carbon with two ORs directly connected to the same carbon. It's an acetal. Yep. Before we go back to the slides, I want to say that this is an equilibrium process. So it's a completely reversible mechanism. So all of these steps can go backwards, they can go forwards. The mechanism I drew is acetal formation. The mechanism in reverse is called hydrolysis of an acetal. You are responsible for knowing the forward and the backwards mechanism for this guy. Good luck. Some important details about making an acetal. If you don't have acid around, you cannot get an acetal to form because you need acid to protonate your leaving group to make it go away. So if there's no acid, you stop at a hemiacetal, stop at the neutral tetrahedral intermediate. But if you do have acid and you make an acetal, that's very nice because acetals are often used as protecting groups because acetals are stable in base. By the way that's worded, that tells me that hemiacetals are not stable in base. When we get back to paper in a minute, I will explain why hemiacetals are not stable in base. But Acetals are stable in base. It's common, somewhat common, especially if you're trying to do it as a protecting group, to use a diol so that you can make a cyclic acetal out of it. We'll see one momentarily. What do I mean that acetals can be protecting groups? Well, if you were trying to synthesize this molecule from this molecule, you might want to use a Grignard, because hopefully by now Grignards are your BFFs and you love doing syntheses with them. Don't roll your eyes at me. If you wanted to synthesize this using a Grignard, you might propose a Grignard attacking an epoxide, like that. But if you tried to add solid magnesium to the reactant you were allowed to begin with, to that alkyl halide reactant, aryl halide reactant, that won't work. Because remember, Grignards react with ketones. So if you ever got any MIGBR to form over here, when you have other ketone molecules in solution, that Grignard will start attacking those other ketone molecules in solution, and it won't give you the product that you actually desire. So how do you fix that? You use a protecting group. Let's draw the protecting group bit on paper, but first let's talk about hemiacetals and why they are not stable in base. We said hemiacetals are not stable in base. So if you have something like this, which is a hemiacetal around, and you add a base, like let's say hydroxide. Certainly if hydroxide does it, a stronger base will do it also. That base will deprotonate your OH of your hemi to give you this. And then you can fold down and kick out your O- of your ether thing to get your aldehyde again. And you kicked out a OMI minus. Well, because of that hydrogen connected here, hemiacetals are not stable in base. But an acetal doesn't have an acidic hydrogen. And some of you may say, but isn't that? No. Remember, this is our hydrogen that was our aldehyde hydrogen in the beginning. This hydrogen is not acidic on this acetal. There are no acidic hydrogens on my oxygens either. So an acetal can survive in base. It can survive in super strong bases like Grignard solutions. Let's see. So remember, our goal was to synthesize, I'm drawing it backwards, I didn't really mean to use this to make this compound. Our goal was to use this to make that. But we said if you tried to squeeze magnesium in the middle there, it won't work. That's no good. Because Grignards react with ketones, and you can't have a Grignard and a ketone in the same molecule and expect it to do what you want it to do. If you ever got any magnesium to squeeze between there, there's still tons of reactants like this that did not have the magnesium squeeze in there. So this starts attacking these, and you get things going awry. This is no good. So what's your solution? What do you do instead? You use an acetal protecting group. What is it that you're trying to protect? Well, ketones react with Grignards. So if we disguise our ketone, then we can get our Grignard to be formed while a ketone is not present, and then we can get our reaction to do what we want to do. So I have drawn a thing here that maybe you understand how it happened, maybe not, I don't know. TSOH, we've seen TSO before. This is tosic acid, toluene sulfonic acid, paratoluene sulfonic acid. It's an organic acid. It's like sulfuric acid that you can donate an H, but it's just got this toluene over here instead, so it's soluble in different solvents when sulfuric is only soluble in water. So you can add an acid, and I chose to add a diol so that I could make an acetal that was a cyclic acetal, so that I could show you what a cyclic acetal looks like. I'm not going to draw the whole mechanism, but I will briefly talk through it now. Protonate the carbonyl oxygen. Attack the carbonyl carbon. Exchange protons to get a neutral hemiacetal intermediate. Protonate the OH that remains on your, what was your O carbonyl oxygen. Protonate your O to make it a water. Let it leave, fold down and let it leave. And then O, that's dangling nearby, attacks your carbonyl carbon. Folds it up, deprotonate, ta-da, here's your acetal product. If you didn't follow along, maybe we can draw it together, but just not now. Once I have this acetal, acetals are stable in base, so I can add my magnesium now and expect my Grignard to form, because I don't have a ketone that's going to disturb the peace. My ketone is disguised. Make my Grignard, add an epoxide first, acid work up next to get here. So it looks like Bart Simpson. Add my epoxide, get me here. Also kind of looks like a little mouse. Yeah. I got my group over here the way I wanted, but I need my ketone to be restored back to its original form. So I need to deprotect my ketone. I need to turn my acetal into a ketone. Acetal into a ketone, that's called hydrolysis. Hydrolysis, acid, water, heat. And I get my ketone back just like it was before. Can you do this synthesis without a protecting group? Nope. So I just showed you how to make a cyclic acetal out of a diol. Can this thing make a cyclic acetal? No, because we've got sulfurs here instead of oxygens. I've got a dithiol instead of a dialcohol. But it can make a similar thing to an acetal. I just get sulfur instead. Yep, that's an S over there. There are 3 carbons bridging my 2 sulfurs together. That's totally illegible, but that's a 6-carbon ring with 2 sulfurs on the same carbon and then 3 carbons up top. That thing is has a little bit different properties than an acetal, but it's made in a similar manner. You could draw the mechanism for it officially. What's cool about those dithiane molecules is they can be reduced with Raney nickel. Raney nickel causes that dithiane to completely disappear. We won't talk about the method of how that happens, but it's a cool little nugget of information that it does happen. Okay, ta-ta.